Welcome to this coding walkthrough. In this session, we'll explore problem number 1020, titled Number of Enclaves. This problem challenges us to analyze a grid and determine the number of land cells that are completely surrounded by water, without touching the boundary. Let's dive in and break it down step by step. This problem asks us to work with a binary matrix called grid, where each cell is either 0, representing the sea, or 1, representing land. The task is to determine the number of land cells that cannot reach the boundary of the grid. A land cell can move to any of its adjacent land cells in the four cardinal directions: up, down, left, or right. If a land cell can ultimately connect to the boundary of the grid, it is not counted. However, if it is completely enclosed by other land cells and cannot reach the boundary, it is included in the result. The output for this problem is a single integer, which represents this count of enclosed land cells. Now, let's move on to some examples to better understand the problem and its requirements. In the first example, the input grid is a 4x4 matrix. It includes a mix of land and sea cells. The output is 3 because there are exactly 3 land cells in the middle of the grid that cannot reach the boundary. These are the cells located at positions 1, 2, 2, 1, and 2, 2. Importantly, these cells are completely surrounded by other land cells and are disconnected from the boundary. All other land cells in the grid either lie directly on the boundary or can connect to it through adjacent land cells. This demonstrates the idea of identifying and counting the enclosed land cells. In the second example, the grid is again a 4x4 matrix, but the arrangement of land and sea cells is different. Here, the output is 0 because all the land cells are either adjacent to the boundary or are connected to other land cells that lead to the boundary. There are no land cells that are fully enclosed by other land cells. This example highlights that when all land cells have a path to the boundary, the result will always be 0, regardless of the size of the grid. To generalize this problem, we must consider several constraints and edge cases. First, the grid dimensions m and n can range from 1 to 500. Meaning we need an efficient solution to handle larger grids. Additionally, the matrix contains only 0s and 1s. Edge cases include a grid with all sea cells, where the result is 0 since there are no land cells. Another case is a grid with all land cells. If the grid dimensions are just one row or one column, all land cells are on the boundary, so the result is also 0. For larger grids, the result depends on whether internal land cells are enclosed or connected to the boundary. Other edge cases include small grids like 1x1 or 2x2. In a 1x1 grid, the single cell is always on the boundary, so the result is 0. In a 2x2 grid, any land cell either lies on the boundary or directly touches it, so the result is still 0. For larger, denser grids, the challenge is efficiently traversing the land cells to determine connectivity, especially given the constraints that m and n can go up to 500. Efficient traversal methods, such as depth-first search or breadth-first search, become crucial to solving the problem within the time limits. To start, let's consider the brute force approach. The intuition here is straightforward. For each land cell in the grid, we try to determine whether it can reach the boundary of the grid. This involves exploring all possible paths from the current cell to see if it eventually connects to the grid's edge. To implement this, we can use either depth-first search, DFS, or breadth-first search, BFS. However, this method comes with significant performance drawbacks. Since each land cell is processed independently, there's a lot of redundant exploration, especially when multiple cells share the same reachable paths. The time complexity for this approach is O, open parenthesis m times n close parenthesis squared, which becomes prohibitive for larger grids, and the space complexity is O, m asterisk n, due to the recursion stack or BFSQ. While conceptually simple, this method is computationally inefficient and not practical for larger grids. Now, let's move on to the optimized approach that focuses on boundary elimination using DFS or BFS. The key idea here is to shift our perspective. Instead of checking every land cell individually, we start by identifying the boundary cells. Any land cell that is connected to a boundary cannot be part of an enclave, so the strategy is to eliminate these cells first. This simplifies the problem significantly. Using DFS or BFS, we traverse and mark all land cells connected to the boundary as visited by converting them to 0s. After this elimination step, the remaining land cells in the grid are the enclaves we're looking for. This optimization drastically reduces redundant computations. The time complexity is O(m*n), as each cell is visited only once, and the space complexity remains O(m*n) for the recursion stack or BFSQ. By focusing directly on boundary-connected cells, this approach achieves both time and space efficiency. Another alternative is the union-find approach, which avoids recursion entirely. Here, the idea is to group all land cells into disjoint sets, with boundary-connected cells belonging to a special group marked as the boundary parent. Once the grid is fully processed, we can simply count the land cells that do not belong to the boundary-connected group to identify the enclaves. This method has a time complexity of O(m*n)alpha(m*n), where alpha is the inverse Ackermann function, which grows extremely slowly and is nearly constant for practical purposes. The space complexity is O(m*n) due to the union-find data structure. While this approach avoids recursion, it can be more challenging to implement, and the logic may feel less intuitive compared to DFS or BFS. Additionally, debugging union-find-based solutions can be more cumbersome, especially for grid-based problems like this. The optimized DFS/BFS approach stands out as the most practical strategy for solving this problem. The key observations driving this method are that any land cell connected to the boundary cannot be part of an enclave, and eliminating these cells first leaves only the fully enclosed land cells. This realization simplifies the problem and reduces unnecessary computations. DFS and BFS are particularly well suited for exploring connected components in a grid, making them a natural choice here. The simplicity, efficiency, and ease of implementation of this method make it the preferred strategy. While recursion depth might be a concern for very large grids, this can be addressed by using an iterative BFS implementation if needed. The final time complexity is O(m*n), as each cell is processed once, and the space complexity is O(m*n) due to the recursion stack or BFSQ. This balanced and scalable approach effectively leverages both the grid structure and the problem's constraints, making it the ideal solution for this challenge. To solve this problem, we need to determine whether land cells in a grid are connected to the grid's boundary. The grid consists of 1s, which represent land cells, and 0s, which represent water cells. Our goal is to evaluate whether any land cell can reach the boundary. To start, we need to identify the boundary cells, those land cells located at the grid's edges. By traversing the top, bottom, left, and right edges of the grid, we collect all boundary land cells into a queue. This step is crucial because it allows us to focus our exploration only on the cells that directly influence the result. By starting from the boundary, we ensure that we are addressing the problem efficiently and systematically. Next, we use either breadth-first search, BFS, or depth-first search, DFS, to explore the land cells connected to these boundary cells. BFS is often preferred here since it processes cells layer by layer, which is helpful for marking reachable cells systematically. Starting with the land cells collected in the queue, we mark each visited cell to avoid redundant processing. For each cell, we explore its 4 neighbors up, down, left, and right. If a neighboring cell is a land cell and hasn't been visited yet, we add it to the queue for further exploration. As we explore, we mark all reachable land cells, either by modifying the grid in place with a special marker, such as changing 1 to 2, or by keeping track of them in a separate visited array. Once the BFS completes, we can evaluate the remaining cells. Any land cell that hasn't been marked is isolated and cannot reach the boundary. Finally, we return the result based on the problem's requirements. This could be the count of isolated land cells, a Boolean indicating connectivity, or some other relevant output. This approach leverages a concept called boundary-first search, which significantly reduces redundant exploration. By limiting our search to cells that can potentially influence the result, we avoid unnecessary computation. Additionally, marking the cells directly in the grid, such as converting 1s to 2s, eliminates the need for an extra visited array, saving memory. This in-place marking is especially useful in large grids where memory optimization is critical. The algorithm achieves a time complexity of O(m*n), where m is the number of rows and n is the number of columns, as each cell is processed at most once. The space complexity is determined by the BFSQ, which in the worst case is proportional to the smaller of the grid's dimensions, O, min, m, n. These optimizations ensure the solution is both time and space efficient. To illustrate, consider the input grid 0100, 1110, 0100. The boundary land cells are identified as 0, 1, 1, 0, 1, 3, and 2, 1. Starting BFS from these cells, we explore and mark reachable cells as 2. After BFS, the updated grid becomes 0200, 2220, 0200. Any remaining 1s in the grid, if present, would represent isolated land cells that cannot connect to the boundary. In this case, there are no isolated cells left, as all land cells are marked as reachable. This final grid clearly shows which cells are connected to the boundary, solving the problem efficiently and effectively. Here, we start by defining a class called solution with a method number enclaves that takes the input grid. The grid is a 2D list representing the map, where 1 indicates land and 0 indicates water. First, we determine the number of rows and columns in the grid. Next, we define a helper function called DFS for depth first search. This function takes the current cell's coordinates, I and j, as input. If the cell is out of bounds or is water, we simply return. Otherwise, we mark the cell as visited by setting its value to 0. Then, we explore all 4 possible directions right, down, left, and up by recursively calling DFS on the neighboring cells. After defining the DFS function, we focus on eliminating land cells connected to the boundary. We iterate over the first and last columns for each row, checking if the boundary cells contain land. If they do, we call DFS to mark all connected land cells as visited. Similarly, we process the first and last rows, iterating through each column to ensure boundary-connected land cells are eliminated. Now, we calculate the number of remaining land cells that are not connected to the boundary. To do this, we initialize a variable count to 0. We iterate through each cell in the grid using nested loops. For each cell, if its value is 1, it means it's a land cell not connected to the boundary, so we increment the count variable. Finally, we return this count as the result, representing the total number of enclaved land cells. Here, we're implementing the solution in Java to calculate the number of enclaved land cells in a grid. First, we define the number enclaves method, which takes a 2D array grid as input. We determine the number of rows and columns in the grid and define a helper method, DFS, to perform a depth-first search. The DFS method is responsible for marking all connected land cells as visited by setting their value to 0. We use a base condition to ensure we stay within the grid boundaries and skip over water cells. To explore the 4 possible directions up, down, left, and right, we define a directions array and recursively call DFS for each direction. Next, we eliminate all land cells connected to the boundary by iterating over the first and last columns for each row and the first and last rows for each column. If we encounter a land cell, we call the DFS method to mark the connected cells as visited. After eliminating the boundary-connected land cells, we proceed to count the remaining land cells that are completely enclosed. We initialize a variable count to 0 and iterate through all the cells in the grid. For each cell, if its value is 1, meaning it's a land cell, we increment the count. Finally, we return the count as the result, which represents the number of enclave land cells, those that are not connected to the boundary. This approach effectively uses depth-first search to solve the problem by first removing invalid land cells and then counting the valid ones, ensuring an efficient and clear solution. To solve the problem of counting enclaves, let's begin with a simple 3x3 grid example. The input grid consists of 3 rows and 3 columns, and the land cells are represented by 1 while water cells are represented by 0. The first step is the initial setup, where we determine the number of rows and columns, and define a depth-first search, DFS, function to traverse the grid. The goal of the DFS function is to eliminate land cells that are connected to the boundary. Starting with the left boundary, we encounter cell 1, 0, which is a land cell. We call the DFS function for this cell, marking it as visited by setting grid 1, 0 to 0. The DFS then explores its neighbors, finding that 1, 1 is also a land cell. We call DFS again for 1, 1, marking it as visited and continuing to explore its neighbors. This process leads us to cell 2, 1, which is also marked as visited. At this point, all other neighbors of these cells are either water or out of bounds, so we backtrack, ensuring all land cells connected to the boundary have been eliminated. Now that we've handled the left boundary, no more land cells connected to the boundary are found on the other sides. With all boundary-connected land cells now marked as water, the next step is to count the remaining land cells in the grid. We iterate through all the cells and find that no land cells remain, as all 1s have been converted to 0s during the DFS traversal. This means there are no enclaves land cells completely surrounded by water. The result is a count of 0, which we return as the final output for this example. Moving on to a slightly larger grid, we'll now analyze a 4x4 grid that contains enclaves. For the larger 4x4 grid, the initial setup is similar. We calculate the number of rows and columns, and define the DFS function. The first step is to eliminate boundary-connected land cells. Starting with the top boundary, we find that cell 0, 1 is a land cell. We call the DFS function for this cell, marking it as visited. The DFS explores its neighbors and identifies 0, 2 as another land cell. We recursively call DFS 4, 0, 2, marking it as visited as well. At this point, all other neighbors of these cells are either water or out of bounds, so we backtrack, ensuring no further boundary-connected land cells are missed. After checking all the boundaries, no additional land cells connected to the boundary are found. The next step is to count the remaining land cells in the grid. Upon iterating through the grid, we find that there are 3 land cells that remain unvisited: 1, 2, 2, 1, and 2, 2. These are the enclaves, as they are completely surrounded by water and not connected to any boundary. The count of these land cells is 3, which we return as the final output for this example. Let's consider one more scenario, where the grid has no enclaves at all. In the last example, we work with a 3x3 grid where every cell contains land. During the initial setup, we define the dimensions and the DFS function as usual. Since all boundary cells are land, we initiate the DFS from each of these boundary land cells. As the DFS progresses, it marks all the land cells in the grid as visited, converting all 1s to 0s. After eliminating all boundary-connected land cells, we proceed to count the remaining land cells. At this stage, no 1s remain in the grid, indicating that there are no enclaves. The count is 0, which we return as the final result for this example. This concludes our walkthrough of the problem, demonstrating how to approach different scenarios effectively. To analyze the time complexity of this solution, we start with the depth-first search, or DFS, traversal. During a DFS call, the algorithm visits a cell, marks it as visited by setting its value to 0, and recursively explores its unvisited neighbors. Since each cell in the grid is visited exactly once in the worst-case scenario, where the entire grid consists of land cells, the total time complexity of all DFS calls is proportional to the total number of cells in the grid, which is O, rows * calls. Additionally, the algorithm performs boundary DFS by iterating through the cells on the outer edges of the grid. This includes the first and last rows as well as the first and last columns. While there are O, rows plus calls, boundary cells, the DFS only explores unvisited land cells, meaning the boundary traversal doesn't add any extra time complexity beyond the O, rows * calls, already accounted for. Together, these steps ensure that all land cells connected to the boundary are processed efficiently. Next, we consider the time complexity of counting the remaining land cells. After all DFS traversals are completed, the algorithm performs a final nested loop over the grid, checking each cell to see if it still contains land, indicated by a value of 1. This step involves iterating through all rows and columns, resulting in a time complexity of O, rows * calls. When we combine this with the earlier DFS traversal, the dominant term in the time complexity remains O, rows * calls. Moving on to space complexity, the primary factor here is the recursive call stack used during DFS. In the worst case, where the grid is a single column or row of land cells, the recursion depth can reach the total number of cells, leading to a worst-case space complexity of O, rows * calls. However, for most typical grids, the recursion depth is limited by the size of the connected components being explored, which can significantly reduce the actual space usage in practice. Another aspect of space complexity is the grid storage itself. The input grid is modified directly during the DFS traversal, so no additional memory is allocated for a separate visited array. This means the space required for the grid is simply O, rows * calls, which is already part of the input size. Overall, the dominant factor for space complexity remains the recursive DFS call stack, leading to an overall space complexity of O rows asterisk calls. To compare this approach to a naive solution, we note that a less efficient algorithm might involve repeatedly iterating over the grid to individually check each cell's connection to the boundary. This redundant processing would increase the time complexity significantly. In contrast, the optimized DFS approach eliminates boundary-connected land cells in a single traversal, ensuring that each cell is processed just once. This makes the algorithm both time-efficient and space-efficient, achieving optimal complexity for the problem. Now, let's evaluate the best, average, and worst-case scenarios for this solution. In the best case, where the grid contains no land cells, the algorithm only performs boundary checks and counting, resulting in O rows asterisk calls, time and space complexity. In the average case, for a typical grid with a mix of land and water cells, the algorithm processes all land cells exactly once during DFS, maintaining O rows asterisk calls complexity. Even in the worst case, where the grid is entirely composed of land cells, the algorithm still visits each cell exactly once, resulting in the same O rows asterisk calls time and space complexity. The justification for this lies in the fact that every cell needs to be evaluated at least once, either during DFS or the final count. Thus, the O rows asterisk calls complexity is not only optimal but also unavoidable for this problem, ensuring that the solution is both efficient and scalable for large grids. When working on grid-based problems like this one, there are a few common mistakes to watch out for. First, not properly handling edge cells can lead to incorrect results, as any cell on the boundary is inherently connected to the outside. It's important to account for these to avoid false negatives in your solution. Another issue is inefficient grid traversal. If you use nested loops to inspect every cell repeatedly, it can significantly increase the time complexity. Instead, approaches like BFS or DFS are more efficient for exploring connected components. A third mistake is modifying the input grid directly. While marking cells as visited directly on the grid might seem convenient, it can lead to data corruption and make debugging harder. A better approach is to use a separate visited array to keep track of processed cells. Finally, forgetting to check all four directions during traversal can result in incomplete solutions. To avoid this, you can use a helper array, such as 0, 1, 1, 0, 0, 1, 1, 0, which makes it easier to systematically explore all possible movements. Another pitfall to be mindful of is overlooking edge cases. For instance, a grid filled entirely with water, grids with no boundary land cells, or very small grids like 1 by 1 or 2 by 2 can expose flaws in your logic. To ensure your solution is robust, always test thoroughly with these corner cases. Now, when it comes to interviews, recognizing key patterns in grid problems is crucial. Many of these problems revolve around concepts like connected components, shortest paths, or island-like structures, and identifying these patterns early can save valuable time. Choosing the right algorithm is also important. BFS is often better for shortest path problems, while DFS is ideal for exhaustive exploration. Both work well for identifying regions, but you should be mindful of the trade-offs. BFS uses extra space for its queue, while DFS can risk stack overflow on deep grids. Lastly, always clarify the constraints with your interviewer. For example, ask about grid dimensions, boundary conditions, and whether modifying the input grid is allowed. It's also helpful to familiarize yourself with related problems, as they often share similar techniques. LeetCode 200, number of islands, is about finding the number of connected components in a grid, which is a common pattern. LeetCode 695, max area of island, focuses on finding the largest connected region of land cells. Then there's LeetCode 463, island perimeter, which requires calculating the perimeter of an island, a slightly different but related task. LeetCode 130, surrounded regions, involves modifying the grid to identify regions completely surrounded by boundaries. And of course, LeetCode 1020, number of enclaves, which you're working on, asks you to count land cells that cannot reach the boundary. By studying these problems, you can strengthen your ability to recognize and adapt to variations in grid-based challenges. Finally, let's talk about alternative approaches you can use to solve this type of problem. One option is union find, or disjoint set union, which is particularly suited for connectivity problems. While it's efficient, the setup and implementation can be more complex compared to BFS or DFS. Another approach is flood fill using DFS or BFS, which is simpler to implement and easy to visualize. However, with DFS, you might run into Stack Overflow issues on very large grids. A strategy called boundary first search can also be valuable. Instead of starting from land cells, you begin exploring directly from the boundary cells. This can significantly reduce unnecessary work in problems where boundary connectivity is critical. Lastly, iterative DFS is an alternative to the recursive version. It uses an explicit stack to simulate the DFS process. This method avoids recursion depth issues, making it safer for grids with large dimensions. Each of these approaches has its trade-offs, so choose the one that best fits the problem constraints. Great job! We've successfully tackled the number of enclaves problem. Remember, mastering grid-based problems builds a strong foundation for technical interviews. Keep practicing, and don't forget to like and subscribe for more insightful tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!